Yeah, welcome everyone to the HI Weekly Research Seminar. I'm Surya Ganguly. I'm an associate professor of applied physics and by courtesy of neurobiology and electrical engineering at Stanford. And I'm a faculty associate director at HI. So I'm thrilled to announce Agrim Gupta. Agrim is a third-year PhD student in computer science at Stanford, advised by Fei Li. And he's part of the Stanford Vision and Learning Lab. Agrim works at the intersection of machine learning, computer vision, robotics, and his research focuses on understanding and building embodied agents, which enables us to involve agents to learn hard locomotion and manipulation tasks in complex environments, and it reveals insights into relations between environmental physics, embodied intelligence, and the evolution of rapid learning. So you're in for a big treat today. And I just want to say, I've worked with Agrim, and he's an absolute pleasure to work with and super fun to talk to, and is incredibly sharp. Before we begin the presentation, a few logistical details. You can use the QR code on the screen, this one right here, to ask questions through Slido, or you can click on the link that will be in the chat window shortly. I'll be drawing questions from Slido after the presentation, and we'll have about 15 minutes or so for questions. And Agrim, thank you so much for, again, thank you so much for joining us, and feel free to share your screen and begin.
Thanks, Surya, for the kind introduction. Can you guys see my screen?
Yeah.
Okay. Good morning, everyone. I would like to thank HAI for inviting me today, and to all of you present in the audience for attending the talk. Today, I'm going to present our work on understanding and building embodied intelligence. This is joint work with Silvio Savarese, Surya Ganguly, and Fei Li at Stanford. Evolution over the last 4 billion years has generated a variety of endless forms most beautiful, starting from an ancient bilaterian worm and culminating in a set of diverse animal morphologies. In fact, animals display remarkable degrees of embodied intelligence by leveraging their evolved morphologies to learn complex tasks. Each organism is well adapted to its ecological niche for survival. In fact, nature is filled with examples of animals who leverage their embodiment to accomplish multiple different tasks. For example, the trunk of an elephant is truly remarkable in many different ways it can be used. Elephants use it for drinking and bathing. They also use their trunks for snorkeling. They are adept in using their trunks for different manipulation abilities, ranging from delicate actions like rubbing eyes and to carrying logs. Finally, they also use their trunks for communication and smell. Moreover, there are particular behaviors that are only possible with a specific morphology. This is wonderfully illustrated by the ability of geckos to climb both rough and smooth vertical surfaces, mainly due to van der Waals forces between their feet and the surface they are climbing on. In order for these forces to have sufficient magnitude, a very intimate contact between the feet and the surface is necessary, and that too at multiple hierarchical scales. And this is achieved only via its morphology. But in contrast to embodied intelligence, which is common in nature, the recent progress in AI has been disembodied. Although last decade has seen tremendous progress in AI, especially in the regime of supervised learning, fueled by the availability of large-scale static datasets like ImageNet, COCO, Visual Genome, and others. These datasets are static in the sense that they represent a snapshot in time. The learned algorithms have no notion of agency, embodiment, or causality. Another popular approach for building intelligent agents is the reinforcement learning paradigm. Here, the goal is to learn a controller that can take a sequence of actions to perform a task. The controller is learned by interacting with the environment. This approach has been quite successful in solving games like Atari, Go, StarCraft, and Dota. And although this is a step forward in terms of moving away from static datasets, the notion of embodiment or morphology is generally abstracted away. And finally, the field of embodied intelligence posits that intelligent behavior can be rapidly learned by agents whose morphologies are well adapted to their environment. Hence, intelligent behavior is a function of the controller, morphology, and the environment. Embodied intelligence takes a holistic approach towards building general purpose intelligent agents which can one day live and work alongside us. Hopefully, by now I have convinced you that why you should care about embodied intelligence. Despite its importance, the principles of embodied AI are not well understood. But what kind of principles or relationships are we talking about here? In their Turing address, Al Newell and Herbert Simon argue in favor of laws of qualitative structure in the context of AI. In fact, in most sciences, quantitative laws are relatively few. For example, F equal to ma or the gas equations. And there are a lot of qualitative laws like the cell theory, the germ theory, and even evolution. There has been some encouraging work in this direction recently in the disembodied setting, like scaling laws for language models and transfer learning. In the context of embodied intelligence, researchers like Brooks, Bongard, and Pfeiffer have shown that morphology can simplify the control problem. Our goal in this work was to understand the relationship between environmental complexity, evolved morphology, and the learnability of intelligent control. Specifically, we focus on two such scientific hypotheses. First, our goal was to understand if there is a relationship between environmental complexity and generalization ability of the evolved morphology. Note here, we are specifically interested in how the morphology can aid or fasten the process of learning a new task. Second, is there an evolutionary pressure to select for morphologies which can learn faster? That is, are the behaviors learned late in the lifetime of early ancestors expressed earlier in the lifetime of their descendants? If some of the terms are not clear right now, I will delve into more details on both of these questions later in the talk. But first, we need to take a step back because in order to understand or even test these hypotheses, we first need a framework which can create embodied agents in complex environments. Moreover, a critical prerequisite is that the framework should mimic the intertwined processes of learning and evolution, which have resulted in the diversity of morphological forms on Earth. The two adaptive processes of learning and evolution operate at two different levels. Learning operates over the level of an individual, wherein an individual interacts with its environment and learns intelligent behavior for survival and reproduction. Similarly, evolution operates at the level of populations and selects individuals who are fittest for the particular environmental niche. In fact, these two adaptive processes also operate at two different timescales, where learning happens over the lifetime of an individual and evolution happens over generations of species. As you can imagine, there are many challenges in creating embodied agents, but here I would like to focus on two main challenges. So the first challenge is that the search space of possible morphologies is combinatorially large, especially given the huge number of possible permutations and combinations of materials, different components, and the different configurations in which those components can be configured. Second, evaluating morphologies that are well adapted to a particular environment is extremely compute intensive, especially when you increase the complexity of the environment. So you have a large search space, and evaluating a particular morphology in that search space is also compute intensive. And when you do both of these in a more challenging process environment, the compute requirement really grows. So in today's talk, I will first discuss how prior work has created embodied agents. Then I will introduce our computational framework called DERL which is able to create embodied agents in complex environments. I will then talk about our morphological design space, which we call unimal design space. And finally, I will discuss the scientific insights which can be uncovered by leveraging DERL. So as I just mentioned, given these substantial challenges, let's first look at how prior work has tackled the challenges of creating embodied agents. The field of evolutionary robotics is at least 3 decades old, starting from the seminal work of Carl Sims in 1994. So in this work, he used directed graphs as genotypes. Each graph contains the developmental instructions for growing a morphology and provides a way of reusing instructions to make similar or recursive components within the agent. Now, this greatly reduces the search space. As you can see in the diagram, if you have this recursive structure, you can only form a certain type of morphologies. So the search space is greatly reduced, but this also comes at the cost of limited expressiveness, as you can only express morphologies which are part of this recursive structure. So as you can see on the right, given these particular rules, very similar type of morphologies, morphological forms emerge. Another way to tackle the challenge of having a large search space is to work upon a set of modular components which can be assembled in different configurations based on specific set of rules. Now, a key advantage of this approach is that since all the components can be manufactured, you can actually create the agents and test them in real world. And that's pretty amazing. But obviously, this comes with the limitations inherent with the current manufacturing technologies. And consequently, you are limited to a very small search space. Another approach or perspective on creating embodied agents has been motivated from the use case of optimizing a hand-designed robot morphology for a given environment. So in this case, you start with a predefined morphology or a base morphology, for example, a fish or an ant or a cheetah in popular physics simulators like Mujoku. And the goal here is that given this base morphology and given an environment like flat terrain, you need to find the optimal parameters of the morphology so that this new morphology can perform the task better. And in this perspective, again, the search space is severely limited because you're basically just optimizing for different limb parameters, like the size or the shape of the limbs, and the overall structure of the morphology is fixed. So you're not going to get any new morphology or a different agent. Now, the second major challenge is fitness evaluation. That is, once you have created the morphology, you need some mechanism to evaluate how good the morphology is. A common solution is to avoid learning the controller via reinforcement learning, as we know that reinforcement learning is extremely sample inefficient. And this can be achieved by using hand-designed controllers, which have predetermined actuation patterns of control like sinusoids. This obviously simplifies the control problem and greatly speeds up fitness evaluation process. Similarly, you can also use model predictive control for simple locomotion tasks. You can also avoid the fitness evaluation by learning some sort of a predictive function. So you can have a graph neural network and you can learn, given a morphology, this graph neural network will output the fitness of the morphology. And this fitness function can then guide your search and greatly reduce the search space. And finally, the third way to speed up the evaluation process is to transfer the learned weights from one generation to another. So this is called Lamarckian evolution. And I will go into more detail about Lamarckian evolution towards the end of the talk. But for now, we can assume that Lamarckian evolution is not a biological plausible way of evolution in nature. And hence, even though this is a valid approach to create agents, if you want to faithfully mimic the processes of learning and evolution, then you can't use this approach. So note that despite all of these heuristics and different ways to reduce the search space or fasten the process of evaluation of morphologies, the prior work was not able to move beyond simple environments like locomotion and flat terrain. So to address these challenges, while avoiding heuristics I mentioned, and still scaling up the complexity of the environment, we introduce a new computational framework, which we call DERL. So DERL is basically a bi-level optimization algorithm, which has two loops. The outer loop is distributed asynchronous evolution, and the inner loop is reinforcement learning from low-level sensory input. So let's first zoom in on the outer loop. Traditionally, the field of evolutionary robotics has used generational evolution as the outer loop. Let's assume you have n workers, basically n compute nodes. Generational evolution proceeds in cycles. First, each worker will create n morphologies, and then in parallel, evaluate the fitness of all n agents. Once the fitness of all agents is evaluated, we will select the top k agents, which will then undergo another cycle of mutation and lifetime learning. As you might have guessed, this creates a synchronization bottleneck, which prevents us from scaling up. If we can somehow remove this bottleneck, we could then scale up the creation of agents. In general, for any evolutionary or genetic algorithm, with lambda being the number of individuals being replaced and mu being the population size, there is a spectrum of possibilities. At one extreme is the generation evolution, which I just described, where the entire population is replaced en masse simultaneously. And on the other extreme, you can just replace one individual at a time. And this is great for us because we can do this asynchronously. So our key insight is to shift to distributed asynchronous evolution. Now, we can have n workers all distributed over a cluster. Each worker operates independently and in parallel. A worker performs tournament selection over 4 randomly chosen agents. So you have a population of agents, and a worker will just randomly select 4 agents from this population. We select the best agent and then mutate it and evaluate its fitness and add it back to the population pool. Now, in order to maintain the population size, whenever we add a new agent, we remove the oldest agent from the population. There are many reasons why you would want to do this. One is basically it results in more diversity. It is also more fault tolerant, and it also avoids us to do any bookkeeping. So the implementation is very simple, and you can do it on like cheap instances on AWS. There are like details about this can be found in method section of our paper. The inner loop in DERL consists of lifetime learning via reinforcement learning. So here you can use any on-policy algorithm, and we use PPO for policy learning. The agent controller takes as input proprioceptive features like joint angles, angular velocities, and also takes task-dependent exteroceptive features like height field, box location, and goal location. So to summarize, DERL consists of the inner loop, which mimics lifetime learning via reinforcement learning, and outer loop, which is distributed asynchronous evolution. In case people have any questions about this part, please feel free to add them on Slido. So now we have this computational framework, but we also need a search space on which this framework can operate on. As I just discussed in the prior work section, we didn't have good design spaces on which we could operate on. So this motivated us to create our own design space, which we called the Unimal Design Space. Unimal Design Space is a short form for Universal Animal Design Space. The goal of this design space was simple. We wanted to have a design space which is expressive and contains as little as possible hand design constraints. So our morphologies consist of 2 types of components. First is a sphere, which represents the head of the agent. And second component is the limb, which are represented as capsules. we have three classes of mutation operations in the design space. So the first is grow or shrink tree. This basically means addition or deletion of limbs. Modify the physical properties of limbs like the shape parameters, radius and height, the density, etc. And modify the joint properties like the degrees of freedom, joint angle ranges, gear ratios, etc. In addition to these mutation operations, we also enforce two constraints. The first constraint is inspired from animals in nature, specifically arthropods. Now, most animals, including humans, are bilaterally symmetrical. We ensure that all our mutation operations lead to morphologies which are symmetric about the sagittal plane. The second constraint is no self-intersections. That is, two limbs cannot intersect each other except at joint locations. This constraint is to ensure that the created agents are physically realistic. So if in theory you would want to 3D print it, it will at least be physically plausible to manufacture them. With these simple constraints, the unimal design space consists a huge variety of morphologies ranging from bipeds, tripeds, quadrupeds, and specifically, if you limit the number of limbs to 10 limbs, you have 10 to the power 18 unique morphologies in this design space. So now we have all the necessary ingredients to create embodied agents, the algorithm DERL and the unimal design space. So let's look at the evolved agents in different environments. So the first environment which we considered was the flat terrain. This is the simplest environment possible and has been the primary focus of prior work. A significantly more complicated environment is variable terrain. There are three types of obstacles here: hills, steps, and rubble. The terrain is created by randomly sampling a sequence of obstacles and interleaving them with flat terrain. So in each episode, we create a new terrain by randomly sampling both the sequence and the parameters of the obstacle. And finally, the most challenging environment out of the three is manipulation in variable terrain. Here, the goal of the agent is to move the box from its initial location to goal location. So the goal location is shown by a red square in the image. And here we not only create a new terrain in each episode, but we also randomly choose a new goal location and box location in each episode. So as you can see, in all of these three environments, the complexity is increasing. And to give a quantitative notion of complexity, you can see that the number of subtasks required to survive in these environments is increasing. So in flat terrain, you only have to locomote on the flat terrain. Whereas in variable terrain, in addition to doing that, you also need to be able to maneuver obstacles. And finally, in manipulation in variable terrain, you have to also do directed locomotion, which is basically reaching the box, and then non-prehensile manipulation, where you have to move the box to the goal location. So here I'm showing agents evolved in flat terrain. As you can see, this agent moved by falling forward, or a lizard-like gait in case of this agent. And this is a perfectly reasonable strategy of falling forward to move as fast as possible. But if you change the environment to variable terrain, this strategy is no longer valid because you have these different types of obstacles. And the evolved agents are generally more stable in the sense they have 2 hind legs and 2 forelegs, and they are not moving by falling forward. So for example, here we have an octopus-like gait on land, which is also extremely stable and can maneuver all of these obstacles. And finally, for manipulation in variable terrain, we find that agents end up evolving arm or pincer or claw-like mechanisms. So for example, this agent has 2 arms, and it is using one of the arms to push the box to the goal location. This agent repurposes its legs as arms to move the box. And again, this agent has 2 arms to move the box to the goal location. Now, given that we have evolved agents in all of these different environments, and we can qualitatively look at the differences. So we saw that some agents had arms, some agents didn't have arms. It would be nice if we could quantify this quantitatively. So a common way to do that is using morphological descriptors. So what I mean by morphological descriptors is different properties of the morphologies. They can be as simple as the width or length or height of the agent. And generally, this has been how morphologies evolved in different environments have been compared. So for example, you can see here in this graph for height, agents evolved in flat terrain in general are tall as compared to agents evolved in variable terrain and manipulation in variable terrain. And this is because if you're tall, you can keep falling forward and moving fast. But that strategy is not valid for variable terrain and manipulation variable terrain, where you have to be short because otherwise you will have to learn a complex controller to be stable. And although this sort of comparison gives you some idea of the differences in morphologies, it does not answer the question whether environmental complexity leads to agents which are inherently more intelligent. In fact, it is also unclear how do you quantify the intelligence embodied in a morphology as a consequence of evolutionary environment. So what do you even mean by morphological intelligence? We basically take inspiration from supervised learning or unsupervised learning literature, where you have huge data set, unlabeled data set, and you perform unsupervised pre-training, which results in a neural network with learned features. And then you use this neural network for supervised fine-tuning on a variety of downstream tasks. And you say that the learned features are better if the performance on downstream tasks is better. So our key insight is that intelligent morphologies should facilitate faster and better learning of novel tasks. Given an environment, you first evolve agents in this environment via processes of learning and evolution. And you have a distribution of agents. And then you take this agent and you throw away the controller. And you train this agent from scratch on downstream tasks. And now, if you compare the performance of these agents on downstream tasks, then the difference has to be due to the morphology. And if certain morphologies result in better downstream performance in terms of better final reward and faster learning, then we say that these morphologies are smarter or more intelligent. Now, in order to evaluate the performance, we also needed to create a suite of tasks to test the capabilities of the agents. Specifically, we tested 3 capabilities, the first being agility. The agility of the agent was measured by different tasks like patrol, point navigation, obstacle, and exploration. So I'll give one example. For example, for patrol task, the agent is initialized at this green sphere location, and it has to move back and forth between these 2 positions. So a morphology which is agile would be better at this task. Similarly, for point navigation, you are initialized at the center of a square arena, and then you have to go to a randomly chosen location in this arena. The second capability which we tested was stability. So in this task, the agent is, in the escape task, the agent is initialized in the center of a hilly region, and the agent has to escape this terrain. And finally, the third capability which we tested was manipulation capability. We tested this in pushing a box over inclined task and manipulating a ball. So manipulating a ball is extremely challenging because unlike the case of box, in case of ball, you have to have precise manipulation abilities, otherwise the ball will roll away. Now, here I'm showing the performance comparison of best agents evolved in different environments. Specifically, let's look at one task here. We take the best agents evolved in flat terrain, so top 10 agents which were evolved in flat terrain, and then we throw away the controller and retrain them from scratch on this new task. And we repeat this for different environments, and then compare the average performance. Here you can see that agents evolved in variable terrain and manipulation variable terrain on average perform better. Similarly, if you repeat this for all the 8 tasks, you will find that agents evolved in more complex environments on average perform better. Now, to test if these agents also learn faster, we reduce the number of environmental interactions. So in the previous case, the agents had 5 million iterations to learn the task, and now we reduce it to 1/5. That is only 1 million iterations. And now the performance gap is even more pronounced. So across all 8 tasks, we find that morphologies evolved in complex environments learn faster. So putting these 2 results together, we find that morphologies evolved in complex environments not only perform better, but also learn faster. So let's look at one particular example. So here I'm showing agents evolved in manipulation in variable terrain, performing the task of manipulating this ball. So as you can see, this agent requires fine control of moving this ball to the goal location. So now let's look at another question. That is, does evolution select for morphologies which learn faster? A common manifestation of fast learning in nature is the existence of innate behaviors. There is a huge variety of complex behaviors ranging from spider making webs, cocoon spinning in moths, swimming in aquatic animals, and nest making in birds, which are innate. And the mechanism of how these animals are able to have such complex innate behaviors had puzzled scientists for decades. One possible explanation was put forward by a scientist called Lamarck. He stated that behaviors learned by an individual within its lifetime can be directly transmitted to its progeny so that they would be available as instincts soon after birth. So concretely, let's say you have a genotype, which is expressed as a phenotype after development, and you do some lifetime learning and your phenotype gets modified to phenotype star. So Lamarck believed that these acquired traits, which I'm denoting as phenotype stars, could be mapped back to the genotype. And if this inverse mapping exists, then you can have this modified genotype, which you can use for reproduction and selection. And if you use this modified genotype, then you can directly inherit the traits which you learned during a lifetime. But we now know that learned traits cannot be inherited like this. Over a century ago, another scientist named Baldwin conjectured an alternate mechanism explaining how animals could acquire these innate behaviors. The key idea underlying his conjecture was that learning itself comes at a cost in terms of energy and time required to acquire skills. So let's consider this example of baby deer. If this baby deer cannot learn to walk early in its lifetime, then it is more likely to be eaten by the leopard. And for that matter, it is more likely to be eaten by any predator. Hence, there is a direct selection pressure on genotypic modifications that can speed up learning of locomotion. So Baldwin concluded that in any environment containing a set of challenges that are fixed over evolutionary timescales, but they also come with a fitness cost for the duration of learning within a lifetime, evolution might find genotypic modifications that lead to faster phenotypic learning. Note that it might seem that the Baldwin effect on surface is very similar to Lamarckian inheritance, but it is strictly Darwinian in nature. And it has also been conjectured that the Baldwin effect can manifest at the level of morphologies. What I mean by that is that evolution might select for morphologies which make learning faster. But as you can imagine, showing this in the natural world is extremely hard. but we can perhaps show this in silico. So let's look at the first graph. Here I'm showing the amount of training iterations required to achieve a particular level of fitness and how it changes over the course of evolution. So in the first generation, you can see that it requires 3 million iterations or more than 3 million iterations for agents to learn to walk on flat terrain. And by the 10th generation, it is reduced by more than half. And this trend holds across all three environments. Across all three environments, we see that the behavior which was required for survival in that particular environment and the time taken to acquire that behavior was reduced by half towards the end of evolution. To get an even better sense of this, let's take a look at a specific example. So here I'm showing training curves of 4 agents corresponding to different generations in the same lineage. So all of these curves belong to the same lineage. So you have in the first generation, the agent acquires a reward of 2000 towards the end of its lifetime. And the same reward can be achieved by the agent in the 8th generation in almost 1/5 learning iterations. And this I'm showing an example of only one lineage, and the average behavior is shown in these graphs. So we have now looked at 2 general phenomena. The first being agents evolved in more complex environments can learn new tasks faster and better. And the second being evolution selects for morphologies which enable faster learning. So we wanted to see if we can mechanistically understand why both of these phenomena occur, and if there is an explanation or a possible hypothesis which we can come up with. So we hypothesize that morphologies that can more efficiently exploit the passive dynamics of physical interactions between the agent body and the environment would simplify the problem of learning a controller. So for example, in the case of flat terrain, we saw that agents which were moving by falling forward, that is a way of efficiently utilizing the interaction between the environment and the body for the purpose of locomotion. And so if you can do that, this in turn will enable better learning in novel environments, which is morphological intelligence, and faster learning over generations, which is the morphological Baldwin effect. And any such intelligent morphology is likely to exhibit physical properties of energy efficiency and passive stability. So we look at these 2 properties as a proxy to quantify if there is efficient agent environment interactions. And if both of these properties are there, if the agent is more energy efficient and passively stable, then that will lead to simplification of the control problem, which would then lead to both of the effects which we see. So let's first look at energy efficiency. We define cost of work as the amount of energy spent per unit mass to accomplish a goal, with lower cost of work indicating higher energy efficiency. This is basically, if you're familiar with cost of transport in robotics or animal location, this is basically a generalization of that metric to different tasks. Because in cost of transport, you have a simple metric of the distance traveled, but in this case, we use the reward so that you can use this metric for any task. So again, here I'm showing how the cost of work progresses over different generations. As you can see here, in the first generation, the cost of work is high. And towards the end of evolution, that is at the 10th generation, the cost of work is reduced by almost 50% in all 3 environments. And this is surprising because we actually don't have any direct selection pressure for energy efficiency. We only select for agents which perform the task better. And this phenomena automatically emerges. Agents automatically become more energy efficient as evolution progresses. Similarly, we look at the fraction of stable population. That is, how much of the population is passively stable. Across all 3 environments, we again find that there is indeed a selection pressure for stability. And in fact, the selection pressure is higher for variable terrain and manipulation in variable terrain, which makes sense because in both of these environments, it is a requirement that if the agent is stable, it will end up performing better. So thus, we saw that over evolutionary time, both energy efficiency and stability improve, which might result in simplification of control. So to conclude, today I talked about DERL, a scalable computational framework for creating embodied agents in complex environments. We then leveraged DERL to unearth two insights. First being environmental complexity engenders morphological intelligence. And second, demonstration of a stronger form of the conjectured morphological Baldwin effect. However, we only scratched a tiny surface in these experiments. And I would like to discuss a few feature directions which we are excited about. So our results can be viewed as a proof of concept that scaling the axis of environmental complexity could lead to creation of embodied agents, which could quickly learn to perform multiple tasks in physically realistic environments. And although we were able to scale the complexity of the environments in this work, the current environments are still very simple. An important line of future work will involve designing more open-ended and physically realistic environments. There has already been very promising work in this direction, like the Excel Land world from DeepMind, where there are hundreds of cooperative and competitive games, or Behavior Benchmark, which has a huge variety of household tasks in physically realistic environment. So it would be exciting to see if we could transfer our learnings to more realistic and open-ended environments. Another aspect is that the vast amount of complexity and diversity on Earth has evolved due to coevolution and competition between organisms, directed by natural selection. In fact, the seminal work by Carl Sims had a simple example of multi-agent evolution, where you had these two agents and the task was to capture the box. And similarly, OpenAI has shown in a setting where the embodiment is abstracted away and you only have a sphere, that if you have this multi-agent curriculum, human relevant behavior can emerge. So it would be interesting if we could combine our learnings in a multi-agent setting. Another aspect is our work also showcases that different morphologies are suited for different tasks. So for example, in flat terrain, you could fall forward and move forward, whereas in manipulation variable terrain, an arm or pincer or claw-like mechanism would be beneficial. And in the real world, this has manifested in a huge variety of robot forms, each with different embodiment and use case. So as you can see here, you have a huge variety of robots. Each robot is specialized for a particular task. And this is in stark contrast with domains like vision and language, where we have pre-trained networks. So in case of robot learning, we always start from scratch. So another question is, can we learn general purpose controllers, which could be used for sample efficient transfer to not only different tasks, but also different morphologies? So this is a teaser result from our upcoming work, where we showcase that for modular design spaces, for example, the Unimal design space, we can indeed learn general purpose controllers. And note that here I'm showing all of these agents are being controlled by a single policy for the challenging task of locomotion on variable terrain. And we show that the learned policy can not only control multiple agents in distribution, but also can control new agents out of distribution and can also result in sample efficient transfer to new tasks. So with that, I'm open for questions yeah.
Okay, great. Thanks, Agrim. I'll give you a round of applause on behalf of the audience. Yeah, so yeah, let's see. Let me go to Slido and let's go down the list. So I guess the first question is interesting one. So you put in bilateral symmetry as a constraint into your universal design space, and nature doesn't have a bilateral symmetry constraint, but it arises naturally from evolution. So if you had turned off the bilateral symmetry constraint, would the optimal morphologies that emerged would they have been bilaterally symmetric anyways? What do you think?
I think there would certainly be some morphologies which are not bilaterally symmetrical and are still able to perform the task. But the majority of morphologies which would have eventually evolved would be bilaterally symmetrical. And you can see that even though nature doesn't have this constraint explicitly, 99.9% of all the arthropods or all the animals are bilaterally symmetrical. So this constraint can also be viewed as us trying to limit the search space. So in case we didn't have that, I'm probably confident that we would have this phenomena emerge naturally, but we would also be requiring probably an order of magnitude more compute because we would be wasting searching for morphologies which we know are probably not that good.
Got it. Thanks. I guess here's a clarifying question. During evolution, you remove the oldest agent, but isn't the oldest agent the fittest one because it survived the longest?
Yes and no. In terms of so, in some sense, aging aging evolution also causes some robustness. So it might be possible that a particular morphological form got lucky in the sense of like for this one RL seed, it was able to perform really well. So the only way to pass on a morphological traits is for the morphologies to be able to retrain successfully to that high level. So if that basic structure and its progenies, all of them are able to get retrain to a higher level, then that trait gets passed on, even if that original morphology is discarded away. And that is what we are looking for, is like structures or priors in morphology which are high performance and not like some random fluke.
Got it. And Vale Gates asked the question, how do you think the DERL approach might influence future robot design?
So I think it depends on what the goal is. If you are focused, if you're hyper focused on, let's say, if you have just one base morphology and you want to just find the optimal components, then you can probably do much more efficient things than DERL, right? Because then you can use all of these heuristics, because then it's an engineering problem and you don't want to waste resources on things which you already know are probably bad. But if you don't have that, and if you have a large enough design space, then I still feel like DERL in combination of some heuristics might be a viable approach. I say that because when you're designing robots, like you actually probably don't want to fully faithfully mimic the processes. In our case, we wanted to do that because we also wanted to like uncover these insights. But if you don't want to do that, you are probably better off by having some sort of more efficient search mechanism.
Okay. I guess I had a question. Scaling laws have become quite famous in language models and in other areas of AI, where they're driving sort of major investments in scaling up models, amount of data, compute, training time, and so forth. In this domain, what's your sense of the scaling laws? So, how much more compute time, evolution time, learning time would you need in order to get how much more new capabilities? What's kind of your intuition based on what you've done? I realize I'm asking you to speculate, of course, but.
Yeah, I tried to do some back of the envelope calculations when I was working on this. Like even though we say that we have scaled up, and yes, we have scaled up in DERL, if you actually compare the amount of compute required for our experiments with state of the art, let's say GPT-3, right? We are probably 3 or 4 orders of magnitude less, even by like scaling up DERL or in this embodied setting. So even with the current peak of compute possible, we are way behind. So that is one thing, and we already see some interesting results. But the second thing is that I think a key limitation is the simulation capabilities, right? So like even if you have all the resources, like for example from OpenAI, when they show emergent behavior, it is still in very simple environments. For example, hide and seek, or for example from DeepMind. So I feel we probably need order of magnitude or two or more compute capabilities than GPT-3 to have something interesting in embodied settings. So imagine like you have like a realistic simulator of the world, and there you're evolving everything. You need that, but you also then need a very efficient simulator. You don't want the simulator to be running at like 60 FPS, which is like what gaming simulators work on. So you want the simulation capabilities also to be an order of magnitude faster. Because if you don't have that, then you will be choked in terms of you will not be able to scale up the learning process. So I believe like simulators like there have been efforts in behavior or iGibson. Those simulators need to be scaled up in terms of simulation speed, and then you also need to scale up the compute access. But it's a couple of orders of magnitude away.
I see. Yeah, actually, during your question, I did a back of the envelope calculation of, how many generations did it take to go from monkeys to humans? And, depending on how you count the duration of generation, it's about 50 to 100,000 generations.
Mm-hmm.
And in your evolutionary simulations, you had 10 generations of evolution, right? So, it's kind of amazing how fast real evolution is in some sense. Like with 100,000 generations, we can go from monkeys to humans. So, I think you're hitting upon, I think, which one of the deepest questions in sort of evolutionary neuroscience is how fast can evolution be? And I think you have a framework to try to answer that, which is super exciting. Another question, it's related to one of your future directions, right? Related to the speed of evolution. We know that evolution can be really sped up by arms races between different species, especially predator and prey, right? So over evolution, predator get better at catching the prey, and prey get better at evading the predator. And that arms race really accelerates evolution. So related to your multi-agent directions, what would be the first kind of arms race between species that you'd like to instantiate to get smarter behaviors, and what would the smarter behaviors be?
I think a very simple starting point would be foraging, right? Like if you have, as you say, predator-prey mechanism, like in some sense, even the hide and seek paper had that, it's like a predator-prey system only. And even that can lead to a huge amount of interesting behaviors. So like one of the things which I did, like an experiment was, there is no multi-agent, but it's like a single agent, and it has to do foraging in this environment. And even there, you can see some interesting behavior come up. Like if you have an agent and it has to, let's say, collect some food pellets, right? Then you would see that on average, the height of the agent starts increasing because I also modeled it as the height is proportional to how far you can see, something like that. And even simple food scenarios like that, the results start to give you interesting behavior. So I believe like as a starting point, the thing would be to just see if you have like this predator and prey or hide and seek kind of mechanism, and then see what evolves. But I also think like an important component there would be to have like realistic vision. So in our case, we simplify the vision by providing the terrain information as height field, but you need to have realistic vision for things like hide and seek to become more interesting. And then you can see, if height or like neck-like kind of mechanisms evolve or not, or like where
I see.
Even sensor placement is interesting, right? Like right now the sensor placement is fixed. So you can imagine that even where to put the sensors on the morphology can be part of the design space. And you can that would also be interesting to see what happens then.
I see, great. Actually, a very practical question from Slido by Gerardo Cardenas. How can we get our hands on the code?
Oh, it is online.
Do you want to advertise how to find it?
Yeah, I can share on it's on my GitHub. I can share on the chat.
Okay, great. So everyone watching the talk can download the code and play around with it, which is fantastic.
Yeah, and we provide Docker container and everything so that the environment setup and all is easy. So it's if you have some compute, then you can run the code.
Some compute. Okay.
Well, you can also run it. Yeah.
Yeah. Okay, so let's see. Okay, so you'll recognize why I asked this question. It's because I know a little bit about your more recent research. But so as you know, HI has launched this new Center for Center for Research and Foundation Models, where a foundation model is defined as a large-scale model trained on very broad data that can be easily and quickly adapted to solve a wide variety of tasks. They've taken off in language and vision, but not so much in robotics or even in simulation. And you touched a little bit upon this, but I'd love to hear more. How might foundation models take off in robotics? For example, can you learn a single model to train all of your morphologies simultaneously? And could you then adapt it to quickly train completely new morphologies? What would such a foundation model look like? And yeah, you know why I'm asking you this question, because you've already partially done this.
Yeah. So I think the way I like to think about it is like it's a spectrum. So if your embodiments are really, really different, so let's say like you have a Roomba and you have a humanoid, I think the only way to share is either world models or what you call pre-trained vision and language models. So if the difference in embodiment is that huge, then I think you will have to operate an abstraction level of these general purpose models, let's say vision or language, and then you can use them to bootstrap learning. But in what we explore is like if you are towards like some middle or towards a spectrum where you have these modular components and you can create robots via these modular robots which can perform a wide variety of tasks. So modular design space provides you a way of this sharing in the space of embodiment. So if you have that, you can still perform a rich variety of tasks, and you can still have morphologies or agents which are well adapted to do different tasks. And then you can basically pre-train a controller which on this huge design space, and we show that it starts to show some favorable generalization capabilities that you can use this controller, and you can just as you do in vision and language, you can start from this pre-trained controller, and it will provide you sample efficiency gains on new tasks and even on new morphologies. And in fact, you can also zero-shot perform a lot of the tasks, or zero-shot generalize to new morphologies.
Interesting. Yeah, you know, that's a similar trick that evolution has used, right? Evolution is nature's tinker. It always recombines modules.
Yeah.
But actually related to that, I believe Gerard Sans asked a question: how important is it in an AI setting to actually mimic evolution? Could other approaches, do better than this interaction between evolution and learning, just for creating AI agents?
I think it always depends on these type of things, right? Like what your goal is. So if you can have a perspective of, I want whatever works, and that's like a engineering perspective, and it's completely fine. And I think then you don't need evolution, probably because like it's extremely inefficient, right? And if your goal is towards the other end of the spectrum to, let's say, understand intelligence or to see how things came to about, or if you believe like, this in sort of emergent behavior, then probably it's a thing worthwhile to explore. So it just depends what your goal is or which camp you belong to. I don't think it's like there's a right answer here.
Okay. So in the last sentence of your paper, you had this intriguing statement, right? That this Baldwinian transfer of intelligence from phenotype to genotype has been conjectured to free up phenotypic resources to learn more complex behaviors like language and imitation. So can you see a pathway to demonstrating the evolution of communication in simulation, or some evolution of rudimentary language, or even imitation, which is simpler and easier to think about, through evolutionary simulations?
I think I have thought a lot about simulating this in terms of language, and because that would be something in multi-agent setting, but also would be simple in terms of like, you don't have to do the whole morphology simulation. You can just abstract away the morphology here and just focus on multi-agent communication. So my hunch is that I think one key requirement you require is stability over generations, right? So language is tricky in the sense that language changes a lot over time scale. So it's not something which is what you call, which has like language itself has evolved. So what I think might happen is like some sort of, I know there are like people who disagree with this, but it might be that what kind of evolves is a ability to learn languages, or like that kind of features get passed on, which enable you to learn language or help you to communicate, rather than specific way to communicate. So the learnability ability gets passed rather than the actual language capability. But this is debated, and
Sure,
language is not my strong suit, so I will not speculate too much here.
Sure, no, but that's fascinating. Okay, thanks so much, Agrim. It was a really fantastic talk, really thought-provoking. Unfortunately, that's all the time we have. Thank you again, Agrim, for joining us, and thanks to our audience for asking such great questions. The topic of next week's seminar is going beyond the here and now, counterfactual simulation in human cognition, presented by Tobias Gerstenberg at Stanford. He's an assistant professor of psychology at Stanford, and you can actually register for that talk through our website, and we hope to virtually see you all there. All right, thanks again, Agrim.
Thank you.